Number 22. Now notice this is the same kind of problem as that one before. We've got 75, each one of these little sections is 25% of our data. 25, 25, 25. 75% of those tests were done before 25% of the paper and pencil. Letter E right there. So that's the answer for that one. So in 23, it looks like this printout is all jacked up. But all we really need is Q1 and Q3 to figure out the outlier. So let me review that. So the interquartile range, if you remember, the IQR is Q3 minus Q1. So let's figure out what that is. And Q3 minus Q1 is going to be 7. All right, so what do we do with this? So we take that 7 and multiply it by 1.5. And that gives us 10.5. What do we do with that? See, there's a little bit, lots of steps, I guess. You say Q3 plus 10.5. If there's any number that's outside of that range, that would be an outlier. So Q3 is 12. So 12 plus 10.5 would be 22.5. 22.5. So any number that's bigger than that is going to be an outlier. So remember, find the RQR, multiply it by 1.5, add it to Q3. Any number that's bigger than that is going to be an outlier. You can also have an outlier on the low side as well. You would just subtract it from Q1, but they look here, greater than, greater than, greater than, greater than. Okay, so usually, lots of times the outliers are going to be on the high side anyway. But anyway, let's go to number 24. So what jumped out at me on number 24, originally I thought it was C right here, but it's the power. When you increase the sample size, you increase the power of the test, which gives you better results. So a smaller size leading to lower power, meaning the first one had lower power, the second one had higher power. Letter A is our answer for number 24. Okay, number 25. We're just trying to write the hypotheses for these. So remember, the null hypothesis is always equal to. So you could cross out letter D and E right away. And we're trying to figure out, so U sub 1 is the group that used the affirmation. So we want that group to have a larger result than U sub 2, the mean of the second group. So we end up with letter C. The affirmation group will have higher scores than the non-affirmation group. That's what our alternative hypothesis is. Let's go to number 26. So let's see. The mean score is 320, 3.2. So I'm going to draw this thing if I can. So the average score was 3.2. And up here at 410, that's at the 85th percentile. So the key here is to figure out how many standard deviations are we above that. So what I do is inverse norm. Inverse norm for 0.85. Let's figure out what that is. And that is 1.03. So it's 1.03 standard deviations above the norm. So we say 1.03 times some standard deviation gives us 0.9. the difference between these two, like that. So we would solve that equation right there. 0.9 divided by 1.03, and you should come out with somewhere around 0.87. That's kind of a tricky question. There are lots of different ways to approach that, but that's the way I did that one. Number 27. Now be careful. It says which one is true. So all of these are false except for one of them. Turns out it's all the way down, letter E. The width of the confidence interval is affected by the variation of the original population. Yes, so we're going to have a larger standard deviation because that's what our variation is, which is going to give us a bigger confidence interval. E is our answer. Let's go to number 28. So, 28. Hiking boots. Now this is kind of matched pairs, right? Because you have the same person doing both things, one boot on each foot for each hiker. So anyway, B is going to be our answer. When we use a matched pairs, it really cuts down on the variation, and there might be a lurking variable, something we did not account for. So that helps reduce that situation. Let's go to 29. So this is kind of a tricky one, or I think they are, because a lot of times I start reading the answers and they all start to sound correct. But remember, we want to stay away from randomization eliminates bias. That's like an absolute. We never do that in statistics. It's always like, sort of, maybe, around. We're going to estimate. That's what we're doing in statistics. Most of the time is just estimating. So anyway, randomization guarantees a more accurate guarantees. We never guarantee anything. So when you take a close look at these, it's going to be letter D. Randomization reduces, okay, it doesn't eliminate. So when we really take a look at this thing, letter D just says that we're just going to reduce the variation. We don't guarantee anything. We don't eliminate anything. We're just going to reduce it and try to make it better. Remember, we're just estimating. Let's go to number 30. So for number 30, we're going to plug these in. See, our humor score is 140. That should go right there. And we're going to plug in 110 for our IQ. Now this side should equal that side, and we're going to see how far off we are when we plug these numbers in. That is what a residual is. Let me do that. So when you calculate this, remember I'm just plugging those numbers in to this formula, we get 140 over here and 149 over here. And remember, it is the observed minus the predicted. In other words, this is the IQ score that we had for that individual, and this, when we plugged it in, no, that's not right. This is the humor score, right? This is the humor score that we actually had. And this is our prediction, given that we have this IQ. So observed minus predicted gives us -9, which is B.